Hello and good day. So this is it, our last lesson for General Physics 1. So this will be the 10th module that you're going to take for this week, the conservation of momentum. So we'll be focusing more on linear momentum and some of the assumptions will be discussed later. But first, let's take a look at this. So are you familiar with this one? So it's what we call the Newton's cradle, no? Hey, how about this one? So yeah, that basically speaks for itself. But the idea is law of conservation of momentum, like any other conservation equations, is that in a closed system, the momentum before an event is the same as the amount after. Well, of course, conservation laws, particularly what do you call this? Is preceded by symmetry. And if you are familiar with mathematical symmetries, you will be very accustomed to why we arrive at conservation laws. So we have another one here. So law of conservation of momentum. So this was stated by Sir Isaac Newton in his groundbreaking work, Principia, or here's the complete name. So the English translation is there, Mathematical Principles of Natural Philosophy, which is what they call science previously, no? Natural philosophy. So you take note of these key terms. So the momentum before is the same as the momentum after. Okay? So translating that into a mathematical equation, so I'm going to include what do you call this? 0 as a subscript for our rho. So by the way, if you still remember, rho is how we define momentum, right? Which is what? The product of mass and velocity. So having conservation law with regards to momentum, so we have initial, which is equal to final, and I just like to include what do you call this, an apostrophe here. So if you're familiar with this variable, or if this diacritic, we call it prime, right? If you still remember in your previous math classes. Now, so I still use sub-zero because I got used to it being used as your initial condition for your initial conditions. You can also write it in a way if you're used to writing initial and final. So rho sub I is equal to rho sub F. Okay, if you're into that thing. But the idea is the momentum before is the same as the momentum after. So after knowing those, let us have an understanding between what is being conserved. No? So let's say you have a car. Okay? So let's say you have a car here. Has a mass. So let's call its mass m sub a, and is going at a certain velocity, right? Which we will call v sub 0. Okay, or specifically v sub a sub 0. So that would be the velocity or the initial velocity of the first mass. Then it will struck, let's say, a certain object. Well, for example, the VLC cone, if you're familiar with that, the orange cone thing we place on the road. We're going to have its mass m sub b, okay, and then its velocity as v sub b sub 0. Okay, so if the car will accidentally bump this, so it will be thrown out, right? So what would be the look of that after? So in that case, your car will still move forward, right? Because of course your car is heavier. But upon bumping on the object, of course, its velocity will be affected because, of course, so that will be v sub a prime. Okay, and then as it still moves forward, your cone will be thrown as well, so moving in this direction. So that will be what, v sub b prime, and still it still has a mass of m sub b. So these are what some of the scenarios. So assuming that the car is coming from this direction. Okay, so assuming that this is your scenario, right? So you get a general grasp of how momentum should be conserved. So these scenarios are what we call collisions. Okay, so very self-explanatory, right? So we're going to focus on two objects colliding, so one object moving and the other at rest, or two objects moving on the same direction, and then finally two objects moving at a different direction. So if they're, what they call this, approaching each other, something like that. In the case of, let's say, what they call that, those vehicles that are counterflowing, that one. So that would be like a great example of collisions that are head-on. Okay, so translating those mathematically, we have inelastic collisions and elastic collisions. So we're going to focus more on inelastic collisions, but of course we're still going to tackle elastic collision. Okay, so first let's have inelastic collision, right? So inelastic collision, so let's go back to the previous slide. So kinetic energy is not conserved. So what means is that upon colliding with, when one object collides with another object, kinetic energy will be reduced. Why? Because it will be transformed to other forms of energy, like for example heat or sound or whatever it is. Okay, so this is like the realistic scenario. And then for elastic collision, this is like the theoretical or the laboratory equivalent, wherein aside from momentum being conserved, kinetic energy is conserved as well. Okay, but we often use this on nearly perfectly spherical objects, like for example billiard balls that are colliding with one another. So yeah, physics is also integrated there, as billiard techniques are applied by using conservation of momentum. So there's that. No, but generally on day-to-day experiences, we often have encounters with inelastic collision. So we have two kinds for that. So we have, let's have first imperfect. Okay, imperfect inelastic collision. So what that means is they don't stick together. So let's say you have this object, okay, then it will be moving to collide with this object. Okay, what would happen would be, what's the definition? They won't stick together. So that means from this initial position, so let's say this is originally your m sub a, it will collide with m sub b, right? And then m sub b, which is originally in this position, will be thrown away as well, usually on the same direction where m sub a is heading. So let's say we're assuming the movement of m sub a is due east, and then m sub b is stationary. So upon collision, m sub a will still be moving on that direction, but at a smaller or at a slower velocity. And then m sub b will be moved. Initially it's at rest, right? But since it was struck by m sub a, so it will be moved as well. So that's what it means for objects not sticking together. So that's what you have to remember. Okay? So what that means? What does that mean? So ibig sabihin, you're going to have a certain mass, okay, having an initial velocity, so that's v sub a sub o, and then you'll be colliding with a second mass with, of course, a certain velocity. Okay, so after the collision, they will not stick together, so that means there will be changes in their velocities as well, both of the masses. So you're going to have m sub a v sub a prime plus m sub b v sub b prime. You got that? Of course, your masses won't change upon collision. I mean, unless you've collided too hard and some of your parts flew away, no? The masses will stay intact. So what would be changing are their velocities. So you're going to notice that initially you have these velocities, then it will be changed after collision. Okay, so this is the mathematical equation of imperfect and elastic collision. So how about perfect elastic? Okay, or perfectly elastic. Perfectly inelastic. Sorry. So we have perfectly inelastic. Remember, this is still under inelastic collision. So what would that mean is objects will stick together, resulting to the same final velocity. So let's say you have, let's have the same example as above. So m sub a colliding to m sub b. So what would happen is that starting from this position, so that's your m sub a colliding with okay, so this is your m sub a, then it will be colliding with m sub b and they will stick together. What that means is they will be moving together on the same direction. So if this is your initial velocity, this will be your final velocity. So what would change is that their final velocity will be combined. So translating that mathematically would look something like this. So this is m b v b sub o is equal to, so you can write this as m sub a plus m sub b multiplied to their final velocity, something like that. Okay, so it's shorter. You got that? Yeah. Then of course we have, elastic collisions. Okay, so as I have stated before, it is impossible to be observed on day-to-day experiences, but we have several rare cases that this can be applied. Okay, so since that's perfectly elastic, so that's perfect elastic. Okay, so remember the key term, it's elastic, as both of the previous collisions are inelastic collisions. Okay, so what would that mean is upon collision, so let's say, after all, I'm always using what do you call this, billiard balls as example. So we're going to use this example. So let's say m sub a is moving in this direction and then m sub b is moving at this direction as well, or let's say they're going to collide with each other. Okay, although this is necessarily not the case. All right, so upon collision, what would happen would be, so of course they will hit each other, right? So upon colliding, so this will be the look of them upon collision, then this will be them moving. So this will be your M sub A, then this will be your M sub B. Okay, something like that. Then of course kinetic energy is conserved for these equations as well. But don't worry, we're not going to have equations that will involve kinetic energy on perfectly elastic unless stated. Okay, so mostly we're just going to deal with velocities, displacement, on some extent force, okay, on solving these problems. All right, so there's that. By the way, the equation for this is actually it's the same as the first one, so imperfect and elastic. Okay, so ma v sub a sub o plus mb v sub b sub o is equal to ma v sub a prime plus mb v sub b prime. There, it's basically the same. All right, so how about we jump on some guided practice problems so we could see how this is applied. Okay, let's take a look. So our first guided practice problem, so let's adjust this. Okay, so we have this. So after a hold up, Robin Banks flees in his 1,575 kilogram getaway car moving at a velocity of 20 meters per second. So he crashes into a 45 kilogram highway barrel which is at rest. Okay, so take note of that. If Robin Banks' car moves at 18.9 meter per second after the collision, how fast does the barrel move after being hit, assuming that it was thrown away? So of course, let's have a really nice illustration for what happened. So we have Robin Banks' car here. So it has a certain mass, so we're going to name its mass A. So zooming at a velocity, which is what we're going to name v sub a sub 0. Okay, then we have a barrel thing according to the problem. So let's draw a barrel there. Okay, so this barrel has a mass of m sub b, which is stationary, so that would be its initial velocity. So upon being hit by the car, so your car is initially in this position. So upon moving, of course it will still move at that direction, so this will be your car now, or I mean Robin Banks' car. Okay, so still having the same mass, and then initially this is the position of your barrel, right? Then of course it will be thrown away. So let's make this 95, so I could draw on some more spaces there. So let's say this is thrown away. So this is now the new location of your barrel, m sub b. Okay, so there you go. So what happened is that they did not stick together, so that's what you need to remember on that. And they're moving on the same direction. Okay, so that means we don't need to account for the signs. Okay, so don't worry, we're going to translate it into equation later. So first, let's write our given. So for our first mass, or m sub a, we have, what's the mass? 1,575 kilograms moving at a velocity of, what's our velocity? 20 meters per second. Okay, and then we have mass for the barrel, which is what? 45, correct? Kilograms, which is moving at, it's not moving, so that's its position. Okay, so this will be our scenario before. So after, of course, you're still going to have the same mass. Okay, but for the velocity of the car, it will be changed to, what would be its velocity now? 18.9 meter per second. There. So now we are tasked to look for the velocity of the barrel. So that would be v sub b prime. Right? So that means our equation would be for inelastic collision. So that would be m sub a sub v sub a sub 0 plus m sub b v sub b sub 0 is equal to, so they did not stick together, so they should be separated, m sub a v sub a prime plus m sub b v sub b prime. There you go. Then upon finding that one out, you can now proceed on writing your solution. I'm going to write it down here. Okay, so m sub a, what's that? 1575 kilograms multiplied by, let's derive the equation first, because we're looking for v sub b prime. So transpose this term to the other side, right? So let's do that. So m sub a v sub a sub 0 plus m sub b v sub b sub 0 minus m sub a v sub a prime is equal to mb v sub b prime. Then since we're looking for v sub b prime, so we're going to divide both sides by m sub b. So cancel this one out. Okay, so this is now your new equation. So we can now proceed on direct substitution. So you don't have to worry about derivation anymore. So let's proceed. So m sub a is 1575 kilograms multiplied by 20 meter per second plus, what's our m sub b? 45, correct? Times 0. Okay, so this is effectively cancelled. Let's use a different pen. Let's have pink. So this is effectively cancelled. So you don't have to include that on your cycle anymore. Then you have minus, okay, m sub a. So this is 1575 kilograms multiplied by, what's our v sub a prime? 18.9 meter per second. There. So this is all divided by, what's that? M sub b, which is 45. So this is all equal to v sub b prime. There. So you can now cancel your units. So you have kilogram on your denominator. So that means all of kilogram units on your numerator will be cancelled. So this one, and this one, leaving you with meter per second as your sole unit, which is what we need because the required is velocity. So let me just grab. Okay, let's solve. I hope you're using your personal cycle as well. Okay. So we have 1575 times 20, right? So that would be subtracted to 1575 times 18.9. Okay, which is of course all divided by 45. Okay, divided by 45. So what's our answer? So what's your answer? Okay, so hopefully you got the same answer as mine. Okay, which is what? 38.5. Our unit is meter per second. Oh, let's check again. So this is 1575. I'm gonna factor it out. 20 minus 18.9. Okay, then divided by 45. There. Oh, there, it's correct. So you can now just box your final answer. Then that's it. It's easy, right? So if you have questions, you just address your subject teacher on the matter. Okay. Okay, let's proceed on the next example. So let's have the second one. So guided practice problem 2. So we have a police car weighing 1950 kilograms going at a speed of 12.5 meter per second. Rear ends a 1500 kilogram sedan moving at speed of 3 meters per second. Okay, then after the collision, they move together as one. So if you're familiar with rear ending, that's bumping the end of the car, then like dragging it. Okay, so it's a really terrible experience, but at least we're going to understand the physics behind it, right? So let's try to draw that. We have our police car here. So let's place a siren, so it will look like a police car. Okay, so this has a mass of something something, so it's moving at a certain velocity. So that would be our v sub a sub 0. Then it bumps the rear end of a sedan. So just assume this is a sedan, alright? I'm not gonna draw it precisely for you. So let's have a smaller arrow for this velocity because this is running slower, right? So after that, they'll be colliding with each other and moving as a single unit. So I'm gonna draw the end result first, okay, because that's easier. Then you have this police car here with the siren. So wing wing wing, moving at this direction, which is our final velocity there. So assuming that they have moved from this position. Wait, this is your sedan, of course. Then this is your police car, rear ending it. It doesn't look like a police car, does it? You get the general sense. Well, just assume that this is a police car, something like that, and it's bumping and it's moving at this direction. Okay, so there's your diagram. Let's now write the given. So for our m sub a, we have, what's the mass of this car? 1950. Okay, 1950 kilograms, moving at a velocity of 12.5, okay, meter per second. And then you have your sedan. Okay, so that's m sub b, which is 1500 kilograms and moving at a velocity of much slower, 3 meters per second. Correct? Okay, then after the collision, they will be moving together. So we are tasked to look for their final velocity, right? Is that right? Anyway, let me just revert back to our previous example here. Yeah, so in this case, you transpose this to the other side, right? This one will be cancelled because this doesn't have a mass thing, I mean a velocity. Alright, the reason why I look back at that is because you're going to see a different approach on this problem. Okay, so our equation here would be course, for what do you call that one? Perfectly inelastic, right? They will be sticking together. Oh wait, let's check. Actually, we can just like look at it here. Right, perfectly inelastic because they will be sticking together. Okay, so there's that. Okay, so you have m sub a v sub a sub 0 plus m sub b v sub b sub 0 is equal to m sub a plus m sub b multiplied by their final velocity. And since this is like straight to the point, you just divide both sides, m sub a plus m sub b, right? And then that's it. Just proceed on substituting. So for our solution, we have final velocity is equal to, what's our m sub a? 1950 kilograms multiplied by 12.5 meters per second plus 1500, right? Kilograms multiplied by 3 meters. Okay, all divided by m sub a. What's our m sub a? 1950 plus m sub b is 1500. There, so now proceed on canceling the units that you will not be needing. So in this case, the masses. Okay, because what we need is what is it that we need? Final velocity. All right, so let's input that on our cycles. So we have what, 1950 times 12.5, then put it inside the parentheses, of course, then plus 1500 times 3. Then that would be what? Divided by 1950 plus 1500. Okay, so you check your input on your cycle if you have written it correctly, or I mean if you have typed it correctly. Okay, just like what I am doing right now, although you can see it. Anyway, so here's our answer. So they'll be moving at a velocity of 8.37. Okay, 8.37. Our unit is of course meters per second. So you just box your answer. And that's it. See, it's really easy. Now we can now proceed on our next example and take a look at some more variation. So for our guided practice problem 3, we have a 980 kilogram sports car colliding at the rear end of a 2,300 kilogram SUV, stopped at a red light. So that's a really important bit of information. So their bumpers locked. Okay, then brakes are locked and two cars skid forward 2.6 meters before stopping. So that means they are moving together, right? So you're going to notice there's different given here. Okay, so you have displacement and then you have coefficient of kinetic friction. So this will be an interesting given. Okay, so let's try to draw that. I'll be drawing generic cars. Okay, so don't expect me to draw a sports car. Okay, so this is your sports car and it's moving to bump an SUV. So let's make the hump of SUV a bit bigger because it's a big car. So you have m sub b, which is what? Stopped, so you don't have to draw an arrow for that. Then this is, so they will be colliding with each other. So I'm going to draw what their final position. All right, so this will be your SUV. Then this will be your sports car. Okay, which has moved a certain displacement. So this is our delta x. Okay, then we have a coefficient of kinetic friction, right? Which is here. There. Then you just draw the imaginary cars here. So since they're imaginary, you just kind of like wing it when you're drawing it. Doesn't really matter as long as you understand the diagram. All right, so this is what moving on this direction. So this is your v prime, since there will be interlocking. All right, so let's try to write our given. So we have mass A at 980 kilograms, moving at a velocity of, oh, there's no velocity. Okay, so that won't be a given. So we're going to have what? Mass B. Okay, which is what? 2,300 kilograms. All right, which is not moving, so that will be your v sub b sub 0, which is 0. Okay, then after that you have what? Displacement. Okay, so that will be delta x, which is what? 2.6 meters. Then you have coefficient of kinetic friction. That's what? Mu sub k equal to 0.80. So we're asked to look for, calculate the speed of the sports car at impact. So that would be the velocity of the car, which is this one. You got that? So what is being asked is, take a look, calculate the speed of the sports car at impact. Okay, so that means we're going to look for this one. Okay, so yeah, so that will be your required. So let's place it here, v sub a sub 0. Okay, so of course we're going to assume constant acceleration for this one, but firstly let's try to explore the equations, no? So first we have perfectly inelastic, right? Because they will be sticking together. According to the problem, there will be locked, both the bumpers and the brakes. So let's have that translated into equation. So that's m sub a v sub a sub 0 plus m sub b v sub b sub 0 is equal to m sub a plus m sub b having the same final velocity. Okay, now we know that v sub b sub 0 is 0, right? So we can just cancel this one. We won't be needing that. Okay, so then now we're left with what? M sub a v sub a sub 0 equal to m sub a plus m sub b multiplied by v prime. Okay, so what can we explore here? So first, we can assume that this will be lower because of course there will be more mass on this side of the equation compared to this side of the equation, right? So what can we explore more? Upon collision, there will be an effect of friction. So let's explore that now. So friction force would be playing a role here. So how are we going to approach that? Maybe we can have, right, what? Summation of forces is equal to applied force minus friction force. Correct? Then or we can just, since the final force for this one is 0 because they will immediately stop moving, so let's just look for friction force instead, which is what? Mu sub k mg, right? And then this will be what? Usable on the other side once they were like sticking together, which is the second side of the equation, or this one, right? You got what I'm saying. Okay, so that will be our approach. So in this case, we're going to treat the summation of this and be included in this equation. Okay, so now we're going to have friction force is equal to mu sub k multiplied by m sub a plus m sub b, because their masses will be combined, times g. Okay, then what else can we do here? We don't have final velocity, but we have distance, right? So what can we do on distance? Let's explore something. So we have displacement is equal to we have acceleration for the third equation, right? But since acceleration is constant, we can just say that it's decelerating, so maybe that would not be very helpful. Let's try now. So we have what? A delta t squared over 2 plus v sub 0 delta t. Then for the fourth equation, we have v squared is equal to v sub 0 squared plus what? 2a delta x. Okay, for this one, this will be cancelled since our final velocity for this one will ultimately become 0. Okay, then for the first one, our v sub 0 here will be the velocity upon impact. Okay, so that will be the speed of the sports car upon bumping to the sedan, right? Okay, continuing, since what I've stated earlier na this initial velocity would be the velocity upon impact, which is of course the velocity of your racing car, how about we try to approach it using work? Now, so since we have stated, I'm going to write it here, work is equal to force times displacement. In this case, we're going to utilize friction force on this one, which is the work caused by the friction force on both of the objects. And then we have stated that work is also what? Mass times velocity squared over 2. Now in this case, we're going to utilize the velocity of the sports car since the other one is not moving, diba? So that's immediately cancelled. Correct? You got my point on that matter. Okay, so knowing those, we can now write what they call this work equation for before and after. So we're going to utilize the usage of momentum as well. So this will become work is equal to rho times velocity, which is in this case our initial velocity over 2. Okay, you got that, since rho is mass times velocity, which is this one. Okay, so we're going to do that. Then our work after will be this equation, but utilizing this friction force. Okay, so because ultimately our velocity will be 0, so we're not going to utilize this equation because there's incompleteness in variable. So here, let's do that. So we have rho, which is what? M sub a V sub A sub O. So that's our rho multiplied V sub A sub O over 2 is equal to, so we have friction force here already. So what do we need is the displacement, which is provided on our given. Wait, is the coefficient correct? Wait. Where's that? Here. 0.80. Okay, that's correct. So we're going to have, so mu sub k multiplied by, of course, the masses of both, because they will be contributing to the friction, right? Multiplied by acceleration due to gravity. So that's the friction force caused by the tires of the two cars, then multiplied by displacement, okay, which is the skid that they will be creating, which is 2.6 meters. Okay, so now we can just multiply both sides by 2 to cancel. So, and then next that we can do is divide both sides by m sub a. Okay, so let's do it here as well. So in that case, we're just going to have v sub a squared on the other side, v sub a sub 0 to be squared is equal to, so just copy everything else here. So this will become 2 mu sub k multiplied by m sub a plus m sub b multiplied by g delta x divided by m sub a. And finally, of course, you just square root both sides, then you cancel this. Okay, sir, why did you approach it with work? Okay, the reason behind that is because we're talking about the impact, remember? And of course, upon that impact, before the release of, before the change of like kinetic energy and everything else, the work at that moment is still the same compared to the previous one. You got my point? Okay, so and of course it makes like a very cohesive equation. So there's that. Okay, so for our substitution, we can now proceed on doing that. So we have v sub a sub o is equal to, so 2 times 0.8, correct, multiplied by, 0.8 multiplied by, what's our m sub a? 980 and 2300. Are those values correct? Okay, those are correct. So we have 980 kilograms plus 2300 kilograms multiplied by acceleration due to gravity, so that's 9.8 meter per second squared, multiplied by displacement, which is 2.6. Is that correct? 2.6. Okay, 2.6 meters. Okay, all divided by m sub a is 980 kilograms. So first, we can now cancel the masses. That's very obvious. Then since this is inside the radical sign, you can now cancel the radical sign as well, and one of the meters and one of the seconds as their unit. So the remaining unit will be meter per second, which is very handy, since what we're looking for is the velocity of the sports car upon impact. So there you go. Just plug those values on your cycle. So what will be our answer? Okay, so you have square root. Okay, square root first, then you have 2 times 0.8 multiplied by 980 plus 2300, okay, multiplied by 9.8, then finally multiplied by 2.6. Okay, all divided by 980. So what's our answer? There you go. The velocity of our car is 11.68 meters per second. So if you're going to look for that in kilometers per hour, which is how we measure the speed of our sports car, so that would be really fast. Okay, so if you have more questions, you can just address your subject teachers on that matter. But for now, that's it. No? We can now proceed on answering the self-paced practice problems. Okay? And then some of those will be discussed to you, especially utilizing perfectly elastic collisions. So you just box this one. And that's it. Thank you, and see you guys next time, right? Because this will be like our final lecture. So that's it. Thank you and goodbye.